In this last section, we're going to talk about conic sections. And conic sections get their name because they're created when you intersect a plane with a cone. And then you get these shapes here that are highlighted in red. And these are your conic sections. Now, typically we think of a cone as this shape when we imagine an ice cream cone, when in reality, it's really two parts back to back like this that are identical. Now, this particular style cone is called a right circular cone. And this is generated if you imagine a line that passes through the origin. So this is your origin right here. And then you spin that line around the y-axis. Then you get this cone. Now, a parabola is formed when your plane intersects the cone and the plane and that line are parallel. So that's when you get this parabola. Then you get a circle when the plane cuts straight across. And then if the plane comes in at a slight angle, but you still keep that full loop, then you get a circle that's elongated, and that's your ellipse. And then when the plane cuts through both sides of the cone, that's when you get this hyperbola. That's this shape here. The first conic section we're going to look at is the parabola. Now, when we have a parabola that's facing concave up or concave down, then we have a quadratic function. When the parabola opens left or right, it's still called a parabola. It falls under that umbrella of that conic section shape. However, it's not a function at that point because it doesn't pass the vertical line test, but it's still a parabola. It's just not considered a quadratic function. So the official definition of a parabola is that it is the set of all points whose distance from a fixed point called the focus, and that's this point right here, is equal to the distance from a fixed line called the directrix. This right here is the directrix. The point halfway between the focus and the directrix is called the vertex. So that's this point right here. So there is a distance from the vertex of P in this direction. That gives me the focus point, and then a distance of P outside the parabola in the opposite direction, and that will give me my line that's called the directrix, whatever, either a vertical or a horizontal line that passes through that point, depending on which way the parabola opens. So if the parabola opens side to side, open right or open left, then this directrix would have the equation x equals and then our value that it passes through. So keep in mind that this can open in different directions. Any point on this parabola, if I come out, let's say to this point here from the focus, then this distance here from the focus to this point will be the same as this distance here from the directrix to that point. Those two distances will always be the same, and that's how this is defined. Something that's not shown on this picture here, which is called the axis of symmetry. The axis of symmetry is the line that passes through the vertex. In this case, it would be a vertical line because the parabola is concave up. If it was facing sideways, then the directrix would be vertical and the axis of symmetry would be horizontal. But in any case, the axis of symmetry is the line that passes through the vertex that cuts that parabola in half. Now, another thing that's not labeled on this chart is something called the latus, L-A-T-U-S, the latus rectum, and that is the line segment that goes from side to side from the parabola that passes through the focus. So from the focus out this way and from the focus out this way, that line segment is called the latus rectum. Now, the distance from the focus along that latus rectum to the point on the parabola, that will be a distance of 2p. And then also on the other side, same thing. Parabolas are symmetric, so it's going to be the same thing on either side. So the latus rectum will be completely a length of 4p all the way across. Now, when I taught algebra class, this is what I called, I know some books call it differently. This is what I call vertex form, but this book calls it standard form. So if I slip up, I apologize. Just know that if I say vertex form, that means this form here. Now, this is what the book calls standard form, and this is where we get our value of p from that we keep talking about this on our graph. And our vertex is going to be at HK, and I'm sure you have seen this at some point in algebra, but we've never actually defined our coefficient that's in front of the x as 1 over 4p. We're getting into some more detail now. So whatever your coefficient is, that's going to be equivalent to 1 over 4p, and then you could figure out what your value of p is. That will tell you where your focus point is and some other things that we just talked about. So here are all the different ways that your parabola can open. If it opens up or down, then we have a quadratic function, and our x minus h quantity is squared. So we're going to have an x squared here. When it opens up, our directrix will be below the vertex. When it opens down, our directrix will be above it. Remember, there's a distance of p from the vertex out. So if my p was 4, then there would be a distance of 4 from the vertex to the directrix, and that would help us determine what that directrix is. Same thing goes with the focus point. If p was 4, then from the vertex to the inside part of the parabola to the focus would be a distance of 4. Now, when the parabola opens side to side, left or right, then your directrix is going to be vertical. Your focus is still going to be on the inside here, and your y minus k is going to be squared, and it's going to be equal to x. So this is when it is not a function, your y will be squared. And then, of course, you can determine your p by the coefficient that's in front of this quantity that's squared. Let's look at our first example. We're going to talk about putting an equation of a parabola from general into standard form. General form is when it's completely expanded. And standard form is when it's in what I call vertex form, when it's factored and you have your quantity squared where you can identify what your vertex is. So this is our general form where we have everything expanded and it's set equal to 0. So to put this in standard form, we're going to use complete the square. So since I see that my x is being squared in this, but my y is not, this helps me identify that this is a parabola. And because it's x squared, I know this is actually going to be a quadratic as well. It's going to either open up or down, concave up or concave down. So what I'm going to do is I'm going to isolate my y term and move everything else to the other side. And then I'm going to try to complete the square with this part here. So I'm going to push the 12 off to the side here because I want to take this x squared minus 4x and I want to use that to complete the square. And then whatever I put in my blank here to complete my square, since I'm on the same side of the equal sign, I need to make sure it stays balanced. So I'm going to add in a negative 4 over here. Whatever I put in here, I have to do the opposite here because I'm on the same side of the equal sign. So to complete the square, I take half of 4 and square, so that gives me 4, and that's why I'm putting the negative 4 here. So I'm really like adding in 0. Now that I have this so that I completed the square, I can factor this. So I have x minus 2 squared. The 12 and the negative 4 add to give me an 8. And so now I have 8y is equal to x minus 2 squared plus 8. Now I can divide everything by 8 to isolate the y, and I get 1/8 x minus 2 quantity squared plus 1. Now, because I know that 1 over 8 is equal to 1 over 4p, according to our formula, 8 must be 4p. So I find that p is 2. Now, looking at this, because this is a positive in front and my x is squared, I know that this is going to be a parabola that opens up. And I know my vertex is at my h and my k, so that's 2 and 1. And one of the most important things here that you're going to identify is your value of p, because that's going to pretty much give you everything you need to graph this out. So my vertex is at 2, 1. Because my focus is a distance of p out from the vertex, and because my parabola opens up, I'm going to come up 2. So that's going to give me the point 2, 3 for my focus. And when I go p down, that will give me my directrix. Now the axis of symmetry is the line that comes up through the vertex that cuts the graph in half. So that's going to be the line x equals 2. And then to see how far my parabola opens up to actually plot a point, since this point right here is 2, 3, I know my lattice rectum comes straight across through the focus from side to side of the parabola. And I know each side of that lattice rectum is 2p. Since my p is 2, I'm going to come out 4 in either direction. So when I come out 4 this way, that lands me at negative 2, 3. And when I come out 4 this way, that lands me at 2, 6. So I can see how wide this opens. Okay, now we're going to look at the conic section, the ellipse. Here's the official definition. An ellipse is the set of all points for which the sum of their distances from two fixed points, called the foci, is constant. So when we look at an ellipse, the longer axis is called the major axis. So in this case, the major axis is going to run horizontally. This is what's called the minor axis. This is going to run vertically. So this is going to be the shorter of the two axes. And then we have the focal point inside here. And the focal point is given to me by the value of c. So wherever the center is, you come out a distance of c in either direction along the major axes. Now, by the definition, it says the ellipse is a set of all points for which the sum of their distances from the two fixed foci is constant. What that means is if I look at this point A and I draw a line to one focus point and then a line to the other focus point, and I add up those two distances, let's say that came out to be, just for an example, let's say it came out to be 3. And then I look at this point right here and I draw a line from that point to this focus point and then to this focus point, and I add up these two lengths, then that length should also be 3 when I add it up. So no matter what point I look at on the ellipse, the sum of the two distances together added up from each of the focus points should give me the same value every time. Okay, so here is what our standard form of an ellipse looks like. And depending on which way the ellipse is facing, if the major axis is running horizontally or vertically, we have two different standard equations where basically you're just looking at the denominators to help you determine that. So what you want to do in this example here of this, these standard forms, my a is going to be bigger than the b, or another way to say that is a squared is bigger than b squared. So when my bigger number is underneath the quantity that has the x, then my major axis is going to run horizontally. Down here, my bigger number is with the y quantity, so that means it's going to run vertically, that major axis. Now the center is always going to be whatever your HK is. And then this is how you determine what your value of C is, so that you come out from the center in either direction to find your focal point. So my center is HK, and then I would come out along the major axes in both directions, whatever the value of C is, and that would give you the focus point. Okay, so looking at this example, here is our ellipse that is in our general form, and we want to put it in standard form, so it looks like in that box up here that we were just looking at. So we're going to complete the square for both of these terms, and then we'll see what we've got. Okay, so what I'm going to do first is I'm going to put my x terms together and my y terms together, since I'm going to complete the square. So my y terms I highlighted in blue, and the x terms I highlighted in red. And so I put those together. So here are my x's, here are my y's, and then I took my constant and pushed it to the other side. Now, out of this, before I complete the square, I need to know that my x squared has a coefficient of 1. So I'm going to factor out a 9 from x squared term and the x term. And so that gives me 9, and then in parentheses, I have x squared minus 4x, and then I have put a plus blank in there because I'm completing the square. I got to put something in there. And then I do the same thing for my y's. I'm going to pull out a 4 from both of these terms. So I have a 4, and then I have parentheses, and then I have y squared plus 6y because I pulled the 4 out of this. And then I left a plus blank in there for completing the square. And then I put blanks on the other side as well, because whatever I put in here, I need to add in on the other side to keep the equation balanced. Now when I take half of 4 and square it, that gives me 4. Now before you run over here real quick and write in a 4 on this side, remember there's a 9 outside these parentheses. So you didn't just add in a 4, you actually add in a 9 times 4, which is 36. So I've got to add in a 36 over here because I added in this 4, which is really a 4 times 9. And then I did the same thing here. I took half of 6 and squared it. That gave me 9. But because of this 4 out here, I didn't just add in a 9. I added in a 4 times a 9. So I have to add in a 36 over here. Now that's just coincidence that these came out the same. That doesn't always happen. So when I clean up this side here, I get a positive 36. And then when I take and finish factoring this, now that I've completed the square, that gives me an x minus 2 squared, and I carry that 9 down. And then when I complete the square here and I factor, I get y plus 3 squared, and then I carried this 4 down here. So now, remember, we're almost there. Remember, when an ellipse is in standard form, this on the right side needs to be a 1. So in my last step, I'm going to divide everything by 36 because I want this to be a 1 over here. So when I divide everything by 36, I get a 1 here. Underneath here, I get a 9 because I get 4 over 36, which is 1 over 9. And then over here, I get 9 over 36, which is 1 over 4. So notice now I have 4, which I can write as 2 squared, and 9, which I can write as 3 squared. And this is a nice example because these numbers come out nice, but remember, even if it comes out to be, say, 5, then your value that you're going to use for squaring it is going to be the square root of 5. So even if this doesn't come out nice, you can still do it. So because this is bigger and it's under the y quantity, that means this is going to have a major axis that's going to run vertically. My center of the ellipse is going to be 2, -3. My major axis is vertical. Now, my major axes, since my center is 2, -3, that's right here. And these values here, my A and my B, tell me the length of my major and minor axes. So because my A here is 3, that means along my major axes from the center out is going to give me my vertices. So from the center, I'm going to go out 3 because that's my value of A. That's going to give me the vertex here. And then on the other side, I'm going to come out A, and that's going to give me this vertex here. Because these vertices are along the major axes, these are called the major axes vertices. So that would be 2, 0, and 2, -6. Now, the minor axis is going to be given by our value of B, which in this case is 2. That's the smaller of the two values. So my minor axis in this case is going to run horizontally. So from the center, I'm going to come out 2 one way and 2 the other way, and that will give me my minor vertices. So that will be 0, -3, and 4, -3. Now, to find the foci, we need to find our value of C. This will be a different formula for hyperbola, so make sure that you're paying attention to which conic section you're dealing with so you use the right formula. But to find your value of C for an ellipse, you use C squared is equal to A squared minus B squared. My A was 3, so 3 squared is 9. My B was 2, so B squared is 4. So C squared is going to be 5, which means C is going to be plus or minus 5. So what I'm going to do is I'm going to start at my center. My center is 2, -3. And I'm going to come down the square root of 5, and I'm going to go up the square root of 5. And that will give me my focus points. So my focus points are 2, -3 plus the square root of 5, and 2, -3 minus the square root of 5. Those are my focal points. Okay, now we're going to talk about hyperbolas. A hyperbola is the set of all points where the difference between the distances from the two fixed points, the foci, is constant. So, like before, when we sat on the ellipse somewhere and we created a distance from that point to each of the foci points, and if we added up those distances, it was going to be constant no matter what point we landed on when we were on the ellipse. So something similar for the hyperbola, we're just going to find the differences rather than the sums, and those differences are going to be constant. So for example, here's one side of the hyperbola, and here's the other side of the hyperbola. If I pick a point, any point on the hyperbola on either side, if I create a line from that point to each of the foci points, whoops, that's a little crooked, but you see what I mean. Okay, so if I take the longer distance and subtract the shorter distance, I'm going to get the same value every time, no matter what point I'm sitting at. So let's say I look at this point right here. If I draw a line from here to the focus point, and then from this point to this focus point, and I find the longer distance and subtract the shorter distance, that's going to be the same value as the previous distance I just found with this point over here. So every one of those distances will always be constant if you take the longer distance minus the shorter distance. Now, when you're looking at a hyperbola, it looks similar to a parabola, like we're looking at two parabolas that are like sitting there butt to butt. However, parabolas and hyperbolas have two different shapes. When I look at a parabola, it's going to be more round when it opens. But when I look at a hyperbola, you'll notice because we have these asymptotes here that cross through the center, the hyperbola, when it opens up, it's going to get more like it's linear rather than more rounded. So that's the difference in the shapes between a parabola and a hyperbola. Now, the asymptotes are going to be based off of our values of a and b. This axis right here is the major axis that runs between the two vertices. Here's one vertice, here's the other vertice. And this is also called not just the major axis, but it's also called the transverse axis. And then here's the minor axis that runs up this way, and that's also called the conjugate axis. So when we go to find the vertices here and here of our hyperbola, that's going to come out a distance of A from the center. So from the center out a distance of A. See how it's labeled right here, A. Okay, now if we go out B, this direction in the opposite direction of the vertices, that's going to create a box, and then the asymptotes are going to go through the corners of the box and through the center point. So when the hyperbola has a major axis that's running horizontal, the slopes of those asymptotes are going to be plus or minus depending on which way it's tilted. Rise, which is B, over run, which is A. If it's flipped the other way, where the major axis is running vertically, then it's going to be plus or minus A over B, because it's going to flip-flop. And then, of course, the asymptote passes through the center, so that will give you a point and the slope so that you can find the equations of the asymptotes. Now, for the foci, if you come from the center out a distance of C, which should be inside the hyperbola, that distance from the center out C will give you where the foci lie. All right, so let's go down and look at what the equations look like in standard form. Now notice this looks very, very similar to an ellipse. The difference is that we have a minus here instead of a plus. Now, because there's a minus here, the order in which we write the terms matters. Not like with the ellipse, usually we do write the x squared term first, but we don't have to do that because it's addition. But with the equation of a hyperbola, there is an order that needs to be maintained because of this minus. Now, if the x term is first, then that means we have a major axis that's horizontal. If we look down here, if the y term comes first, then that means the major axis is going to be vertical. We have our equation here to find our value of C. For the ellipse, it was C squared is equal to A squared minus B squared, but now for the hyperbola, we have C squared is equal to A squared plus B squared. So make sure that you're using the right formula because it's so similar, it's easy to mistake one for the other. Now, when you are looking at a hyperbola that has a horizontal major axis, here's a formula given to find the equation of the line. You can just, if you know what these values are, you can just plug them in here, or you can find it by hand, where if you know what the center is and you know what the slope is, you use the point and the slope to find the line. Same thing down here, but like I said, if it's facing, if the major axis is running vertically, your slope is going to be A over B rather than B over A. See the difference here? So be very careful and make sure that you pay attention to that. Putting the hyperbola in standard form. Here it's given to us in general form. So I want to make sure that I collect my x's and y's together so I can complete the squares. And I'm going to move this negative 124 and push it to the other side. So here are my x terms. Here are the y terms. I'm going to factor out a 9 out of the 9x squared and the 36x so that I can complete the square. So that leaves me with 9 times, and then in parentheses, x squared plus 4x plus, and then my blank for my complete the square. Here, I'm going to factor out a negative 16, and that will leave me with inside the parentheses y squared minus 2y, and then a plus blank for when I complete the square. So I'm going to take half of 4 and square it. So that's going to go here as a 4 for my complete the square. But I didn't just add in a 4, I added in a 4 times 9, so I got to make sure I put in this 36 over here, not a 4. And for this one, I'm going to take half of 2 and square it, that gives me 1. But I didn't just add in a 1 because the 16 is out here. I added in a negative 16 times 1, so I'm going to add in a negative 16 over here. When I combine all of these, I get a 144. And then when I factor what I just did to complete the square, this will give me x plus 2 squared, and I bring down the 9. This will give me a y minus 1 squared, and I bring down the minus 16. And then, of course, I have this 144 over here. And now I want to make sure that this is a 1 so that it's in standard form. So I'm going to divide everything by 144. And when I do that, I get 9 over 144, which reduces as 1 over 16. I get 16 over 144 here, which reduces as 1 over 9. And then, of course, now that I've divided both sides by 144, I have my equals to 1. So it's set up where I have an x term minus something with y in it is equal to 1. And so because my x plus 2 quantity, this term here comes first, that means I'm going to have a horizontal hyperbola. My major axes or my transverse axes is going to run horizontally. So my A is going to be 4. My B is going to be 3. And so, and my center is going to be HK, which is negative 2, positive 1. There's my center. And so to find the foci, I'm going to use C squared is equal to A squared plus B squared. When I do that, I'm going to find that C is 5. And then because it runs horizontally, I know that my slope is going to be plus or minus B over A, which in this case is going to be plus or minus 3/4. And my center is going to also be on the line because the asymptotes have to pass through the center. Asymptotes are going to be y is equal to plus 3/4 x plus 2 plus 1. And y is equal to minus 3/4 x plus 2 plus 1. So that's these right here with the dashed red lines. Okay, those are my asymptotes. So that's what the hyperbola is getting closer and closer and closer to. Now, my center we said was negative 2, 1, so that's right here. My transverse axis runs this way. So to find my vertices and my foci points, I need to come out from the center in either direction. For my foci, I need to come out 5 in each direction. So when I come out 5, when I come out 5 this way, I get that one focus point is 3, 1. And when I come out from the center 5 this way, I get that my other focus point is negative 7, 1. Now for my vertices, I got to come out in A, this direction A in both ways. So I'm going to come out 4 this way and 4 this way, which will leave me with the points negative 6, 1 and 2, 1. Those will be my vertices. Now we're going to talk about eccentricity. And eccentricity is just a number, and we label it as E for eccentricity. And the number basically tells us the shape of the conic section. Now, when E is 0, then the conic section is going to be a circle. And as the E gets bigger, then the shape is going to change. So when we start at 0, as E gets bigger, if it's still less than 1, then it's going to be an ellipse. When E is equal to 1 exactly, then you're going to have a parabola. And then when E gets over 1, then the conic is going to be a hyperbola. Now, the way that the E is calculated, you take two distances and you divide them and you get this ratio. Now, the two distances are from a point to the focus. That's the first distance. And then you divide that by the point to the directrix. So the line that's perpendicular to the directrix. You're going to find that distance and you're going to divide. Now, when you're looking at a parabola, if you take the distance to the point and divide it by the distance to the directrix, by definition of the parabola, that's why E is equal to 1, because we know that these distances are equal. But when E is between 0 and 1, it's an ellipse, and then as it gets greater than 1, it's a hyperbola. Now, we know that it's exactly 0 for a circle. We know that when E is equal to 1, it's a parabola. So when you've got the situation where it's an ellipse or a hyperbola, you want to take the value of C and divide by A. So let's look at an example. We're going to determine the eccentricity of a conic section. So here's our ellipse. I know it's an ellipse because I have a plus here and it's equal to 1. And so I know that my center is going to be 3, -2. And I can identify what my values of A and B are by looking in the denominators. When I look at an ellipse, I know my value of A by taking the square root of the bigger number in the denominator. So A squared is 25, so A is going to be 5. This is going to be my B squared, so my B is going to be 4. And then to find the C with an ellipse, I take C squared is equal to A squared minus B squared, which in this case gives me 9. And then when I square root both sides, I get C is equal to 3. So to find the eccentricity, I want to take C over A, and in this case, I get 3 over 5, which is 0.6. Now, as this number gets smaller and closer to 0, the shape of the ellipse is going to close in and get more round like a circle, and then as you get closer to 1, it's going to become more elongated. So for finding the eccentricity of a hyperbola or a ellipse, you want to use C over A. Our last example, we're going to go through on how to identify conic sections when it's written in polar form. So we have conic sections written in polar form is going to look like this, or it's going to look like this. The E here represents the eccentricity. And then when you have cosine down here in the denominator, then that means your major axis is going to be horizontal. When sine is down here, that means your major axis is going to be vertical. And you can determine what the conic is based on your value of E, your eccentricity. Looking at this equation here, I have 3 over 1 plus 2 cosine theta. So 3 is going to be equal to E times P. E is 2 here, so I know that P is 3/2. And because this is cosine down here, I know that my major axis is going to be horizontal. Now, because I've identified my value of E, and E is 2, since 2 is greater than 1, I know that this is going to represent a hyperbola. So the question wants us to identify it. Let's see. Identify it and then create the graph. Now, rather than doing this by hand, I know you guys can all plot by hand. I think it's a good idea to practice doing this on the calculator. So because this is in polar mode, you want to make sure you're in polar mode in the calculator, which means when you hit y equals, you should see your r's and your thetas, okay? So I'm going to plug in this equation, 3 divided by, and then I'm going to put 1 plus 2 cosine theta, and close my parentheses. Make sure that you have 2 parentheses here because you have the closed parentheses for theta, but then you should have the closed parentheses for the entire denominator. Now I'm going to start with zoom 6, which is our zoom standard from minus 10 to 10 on both axes, and we can adjust it from there if we need to. There's the hyperbola that we just identified. Okay, now that we've graphed it, even though the question doesn't ask us to do this, I think it's a good idea just to practice to put this in rectangular form, and then we can actually identify some of the major features of the graph from the rectangular coordinates as well. These are the resources that we have here to help us translate it into rectangular form. So the first thing I did, I actually had to try a couple different things before I got it to work. But when I got it to work, what I did in my first step is I cross multiplied. So I got r plus 2r cosine theta is equal to 3. Then I replaced r with the square root of x squared plus y squared. R cosine theta is equal to x. So this became 2x, and then I have is equal to 3. So now I have everything in terms of x and y, but now I have to put this in standard form so I can identify everything. So I moved the 2x to the other side. I subtracted 2x from both sides, and I got this. And then what I did is I squared both sides so I could get rid of the square root. So I got x squared plus y squared is equal to, and then when I squared this, I got 9 minus 12x plus 4x squared. So I subtracted x squared from both sides so I can combine my x squared. So I got 3x. I still have minus 12x. And then I subtracted y squared from both sides. And I got minus y squared. And then I subtracted 9 from both sides so I can get my constant by itself. And then I set it up so I could complete the square. Now, I don't have another y term in here, it's just y squared, so I don't have to complete the square for this, but I do have to complete the square for the 3x squared minus 12x. So the first thing I did to help me do that and get rid of this 3 in front, remember when we complete the square, we want a 1 as the coefficient of x squared. So I divided everything by 3, and I got x squared minus 4x minus y squared over 3, and then of course is equal to negative 3. So I just divided all of this by 3. And then I completed the square. So here's my blank. So I took half of this and I squared it and got 4. So I added 4 to the other side as well. So then I could factor this, and I got x minus 2 squared. And then I carried over the minus y squared over 3. And then negative 3 and 4 gives me 1. So I have x minus 2 squared over 1. So my a is going to be 1. And then I have minus y squared over 3. So my b squared is 3. So b is going to be the square root of 3. My center is going to be 2, 0. So now when I pull that calculator picture back up, we can verify that we have the right information. So we have a center of 2, 0. It's horizontal major axes, and I know that because, remember, if the first term in the hyperbola equation, when it's in rectangular form, if that's x quantity, it's going to be horizontal. And then if it's y quantity in front, the y terms, then it's going to be vertical. In this case, it's horizontal. And our A is 1, which means from the center out, I'm going to have my vertices 1 unit from the center out. And then if I wanted to find my foci, I would just go from the center out the square root of 3. I think it's worth the time to practice going back and forth between rectangular and polar so that you can recognize and verify that these graphs are the same. Now on this last page, when you have your conic section in general form like this, we can identify the conic sections by checking these conditions here underneath. So now in our toolbox, we have ways to identify it when it's in standard form. We have ways to identify the conic section when it's in general form. And then we also just went over how to identify it when it's in polar form.